Now in the last video, we have been introduced to the ideal gas equation, and then also how we can make use of the ideal gas equation to derive equations when there's a change in state of a gas. Okay, that led us to learning the different gas laws, the ABCD gas laws. Now in this video, we're going to focus on how we can use the equations to produce graphical plots in the change in state, for the different change in states of a gas. So a very quick recap. For a fixed mass of gas at constant temperature, we are looking at Boyle's law. Boyle's law, we learned that the pressure is inversely proportional to the volume. Then at constant pressure, we are looking at Charles' law, where we learned that the volume of a gas is directly proportional to the temperature. Now whenever there are relationships, we can illustrate it using graphical plots. So when most probably in your lessons, when you learn about Boyle's law and Charles' law, there will be many graphs given to you. These are some examples of the graphs. Okay, so some students may want to memorize the graph for each law. So they remember that for Boyle's law, okay, the graph looks like this. Okay, because pressure is inversely proportional to volume, so we are looking at a y equals to 1 over x graph. And then since for Charles' law, the volume is directly proportional to the absolute temperature, so it's equals, the graph looks like a y equals to x graph. Now that's one way that if you really want, you can memorize. However, there are many variants of graphs that you can encounter that you can be asked to plot. Okay, so if you just memorize blindly, it's going to be difficult when you encounter the non-conventional graphs. For example, you may be asked to plot PV against P at constant temperature. And then you'll be thinking, oh, I didn't see that graph in my lecture notes at all. Okay, or P against density, P over density against relative molecular mass. Even worse, okay, because this is not under any of the gas laws. Now to approach such plots, there's actually a universal method that you can use. The universal method goes like this. So you always start with the ideal gas equation, PV equals to nRT, and then you manipulate the equation until the y variable that you're supposed to plot is on the left of the equation. Now what do I mean by that? So over here, we are asked to plot pressure over density against something. So I'm going to manipulate the equation until I have P over density on the left hand side of my equation. So I'm going to start with PV equals to nRT. Again, to convert to make density appear, or to make relative molecular mass appear, we need to convert number of moles into mass over molar mass. And then to make density appear, we need to bring volume over. Okay, that will give us this particular equation, rho RT over MR. Okay, and since we are asked to plot pressure over density, I'm going to move density over to the left hand side of the equation. Okay, so this is the final equation that you should be using to either analyze your plot or to plot your graph. Okay, where the y variable is on the left hand side of the equation. Now once you have done that, that's half the battle won. You need to find out where is the x variable in the equation. There are three possible scenarios. Scenario number one, for example, if I want to plot pressure over density against temperature, you'll find that temperature appears on the numerator in the equation on the right. So what it means is this, that you have a y equals to x type of graph. So you will look something like this. The second scenario is this, that the x variable is found in the denominator. For example, plot pressure over density against relative molecular mass. So relative molecular mass actually appears in the denominator. So what it means is that you have this kind of relationship, y equals to 1 over x. So the graph is going to look like this. And the last scenario is this, that the x variable is nowhere to be found. So for example, if you are asked to plot pressure over density against pressure, but if you look at the right hand side, there's no pressure there. So what it means is that you have this type of graph, y equals to k, where k is a constant. So let us go back to the earlier example where we were asked to plot PV against P at constant temperature. So once again, the trick goes like this. Start with the ideal gas equation. Manipulate the equation until your y variable, which is PV, exists on the left of the equation. So there's no need to manipulate at all. PV is already on the left. Okay. Next, look for the x variable in the right hand side of the equation. The x variable is pressure. If you look at the equation on the right, pressure doesn't exist in the equation. So what it means is this, that if you plot PV against P under constant temperature, it will be scenario number 3, where it is y equals to k. Now, one very important thing to bear in mind when you are looking at graphical plots, especially when the temperature is in the x-axis, is to look out for the units of temperature. Why? Is because when we look at the ideal gas relations, we are looking at absolute temperature. So if temperature is in terms of kelvins, then yes, your y variable will be directly proportional, meaning it passes through 0. All right, but if your temperature is in degrees Celsius, bear in mind that it doesn't pass through 0, because it passes through absolute 0, which means that if you are looking at degrees Celsius, it's actually minus 273 degrees Celsius. So when you're looking at graphical plots where the x-axis is temperature, bear in mind to check the units of your temperature, whether it's kelvins or degrees Celsius. Now let us look at this question. So in this question, you're looking for the correct graphical plot of pressure over density versus temperature. Okay, so if using the approach earlier, you should arrive at this particular equation. Pressure over density equals to RT over relative molecular mass. So again, the x variable exists in the numerator, so it is the graph will look like a y equals to x graph. Okay, but very importantly is to take note again that the temperature is in degrees Celsius, so it's not in kelvins, so therefore it shouldn't pass through origin. All right, so in this case, the common mistake that students may, even assuming that you can arrive at the correct plot, the careless mistake would be to put the correct answer as A. That's when you don't notice that the units is in degrees Celsius. So given that the units of temperature is degrees Celsius, the correct answer is B instead. So in this question, once again, we are looking at the plot of PV against P. We have seen earlier that this will give us a y equal to K, so a constant across the different pressures, so that will allow us to eliminate A and B. Okay. However, how do we know whether C or D is correct? We need to look at the equation. PV equals to nRT. So at a higher temperature, PV would have a higher value. So since T1 is more than T2, it means that option C is the correct answer.